Okay, yes, so I'm here today to talk to you about the survey observation results of the Open Time Key program Dunes. This was going to be the final results, but I was told that that's a bit too absolute, and not willing to trade my blue laser pen in for a red one, I decided that I'd stick to just the survey observation results. So this is the result of the consortium, and behind every survey is a whole load of people, and to identify a few characters here, have people in bold are here at the conference, so find them, talk to them, understand what contribution they've made to the presentation they make. Carlos is the PI, so without him, none of this would have happened. And the guys in blue over here, they've all got poster presentations, so I encourage you to go and check out their results, except for Steve's, because that's not based on Dune's data. So, Herschel Dunes. 133 main sequence, sun-like stars in the solar neighborhood. This is volume limited, so I will be using Hipparcos numbers to identify these targets, and I apologize to our transatlantic brethren for that. But in addition to the volume limited section, we have a few interesting targets within 25 parsecs, and these include sort of some Spitzer debris disks and also some exoplanet host stars. And in addition to all those that we took for ourselves in Dunes, though we also share a large number of targets with another Herschel Open Time program, Debris, and we'll only be concentrating on the Herschel data in this talk that Dunes took directly. So what was our scheme of attack? It was to try and measure the photosphere of all of our 133 targets with a signal to noise of around 5 to 10. This dropped to a signal to noise about 3 to 7 due to the PAX noise being a little bit worse than we'd hoped. But still, in every case, we do measure the photosphere of our target at 100 microns. So we've accomplished our objective, which gives us a very good constraint on the presence of dust around all of these stars. So moving on, this is the slide you have to pay attention to. Not important numbers are distance within 20 parsecs. So this is kind of a sort of quasi-de-biased version of the total aggregate results from the survey, the 133 stars, only the stars within 20 parsecs. The important lines here are that in terms of non-excess, large number of stars are non-excess stars, which is kind of disappointing, but there's no take-backsies, unfortunately. And here, in the excess sample, we have, within 20 parsecs, we have 25 stars, incidence of 20%, and that is invariant to the spectral type, unlike previous results, and we think that's a result of having gone straight to the photosphere for all of our targets. Most importantly, at the very bottom here, you see that the number of stars we've got which have resolved debris disk, or at least extended emission on the major axis, we have 16 of our targets, and that's 13 brand new ones, which demonstrates the power of the higher angular resolution of the Herschel Space Telescope over previous observatories. And that allows us to do a lot more complicated and detailed modeling than was previously possible with these kind of objects. So, for all those non-excess stars, they're not entirely useless. So on the left here we have non-excess, and these are upper limits, 3 sigma upper limits in fractional luminosity in units of 10 to the 7 times the actual fractional luminosity. So this is 10 to the minus 7, 10 to the minus 6, and 10 to the minus 5. The red dots are K stars, green are G stars, and blue are F stars. And you see generally we get a trend. So you can see fainter dust around hotter stars, obviously. And on the right-hand panel here we have the actual excess emission we see from our excess debris disk stars, and there's no real trend there, but it again looks pretty impressive. I should point out that the reason we use 37 Kelvin rather than any other temperature is that gives us the lowest limits from PAX, and so for example at MIPS it would have been 50 Kelvin to do the same thing, but we choose 37. So, okay, you've got a lot of non-excess stars. What can you do with them? You can pull them up into a nice Gaussian plot, and yep, we get a little shift here between the 0 point and where our peak in the aggregate plot is. This, we think, it's been seen before. It was in the 70 micron from Spitzer MIPS in Hillenbrand et al. 2008, but we see this is 100 microns. And so we see a lot of, we see a little shift that's sort of slightly underestimate, our fluxes we observe are slightly underestimated compared to what we'd expect to get if we're extrapolating from the near-infrared optical fit to the stellar photosphere model. And the best example we've got of this is nearby star Alpha Cen. This is Alpha Cen A. and we've observed there is a deficit between the extrapolated flux we would expect from the model, basic model, and what we actually observe. And this is the first direct observation of the infrared minimum, temperature minimum of a stellar photosphere other than the sun. And we've done the same thing for Alpha Cen B now, and that's currently in prep. So every SED tells a story, and these are 4 very different stories. In the top left here we have HIP 4148, and you see the light blue dots are the optical near-infrared and ancillary data. The purple line is the IRS spectrum, and the black line is the photosphere model fitted to the optical near-infrared and WISE 1, 3, and 4 flux points. You see here, this is the MIP 70 point, and this is the PAC 70 point. They're quite different, and this is due to the presence of 3 galaxies neatly equidistant around the debris disk star. So the Spitzer flux was quite contaminated, but fortunately, with the high resolution PACs, we can get rid of some of that, and it's still a debris disk star. So that's a happy result for that one. But unfortunately, as you get to the lower angular resolution at longer wavelengths, the contamination starts to creep back in again. So we need a bigger telescope. Moving on, you have, again, similar results. Unfortunately, most of our stars are bright, so the quality of the JHK from 2 mass is usually poor, and therefore that's not a great, that's why we try and rely more on the mid-infrared measurements to scale the photospheres rather than the near-infrared in this case. And this gives us a nice example of debris disk rising with the IRS spectrum off the photosphere model and falls off neatly as you would expect it to if you have nice simple models. But we don't just take PACS data, although that's what I've concentrated on, what I've explained to you so far. We also use SPIRE, which is a sub-millimeter instrument, also on Herschel, which expand our wavelength range from out to 500 microns, covering another 3 bands. So up here we have HIP 107649, another nicely resolved debris disk. I'll show you a picture of it in a bit. And we get a nice full wavelength coverage all out into the sub-millimeter, and do some great constraints on that. And finally, unfortunately, the confusion limit was quite high on SPIRE, about 7 millijanskys. So for most of our disks that we took sort of 20 images of disks we thought we'd be able to get some data on with SPIRE for constraining the sub-millimeter slope. But unfortunately, most of the time we just got upper limits. So unfortunate, unhappy ending there. So extended emission, this is what we really want. And here you go, PAC 70, 100, and 160 micron images. And sort of once you've got a nice resolved ring, you can do a stellar subtraction, and then you can deconvolve it by a million different ways. And I encourage you to go and look at Torsten's poster to understand what he did and what we found out from that. Unfortunately, most of our disks weren't as well resolved as this, and therefore we ended up with sort of some interesting shaped lozenges, which are still extended compared to the PSF model here. You see the black PSF model is in black, the minor axis is in blue, and the major axis is in red. The dashed lines indicate the 1 sigma uncertainties in the radial profile fit at 100 and 160 microns, and you have comparably the images here to compare to. And yeah, we can still do the similar kind of modeling with them, but it's not quite as photogenic, unfortunately. So moving on, and even worse, so that was this is the 4th of our top targets. I'm not going to go through all of them in line, don't worry. But we have here, it's sort of 70 microns here, this kind of slight point-like kind of blob here. 100 microns, it's slightly more extended, and 160 it looks even more blobby. And then at 160, so 250 you go, oh god, there's a galaxy in the back right there. But as you see, it's neatly fitted by a single temperature black body, just about, in the data, but the radial profiles tell a different story. And this is being worked on by Steve Ertel, so I encourage you to go and talk to him about this and see how the modeling has managed to disentangle the structure of that particular system. So, other results, some of these have been published, you stop me if you heard this one, but actually don't. But we've got steep SED, so you see this in the sub-millimeter, you see the steep fall off, steep in the kind of black body, that's due to grain size and the particle size distribution. But we're seeing this in the far infrared at sort of between 100 and 160 microns, seeing a very steep fall off, and this is believed to be either due to a very steep non-collisional equilibrium particle size distribution, so a very steep particle size distribution slope, or it could be due to having a very small upper grain size in these systems, either of which which needs to be disentangled between those two possible options. And furthermore, yes, these controversial cold disk candidates. So no excess at 100 microns down here, 1700, barely off the photosphere at 100, but you've got this kind of clear excess at 160. And these are a bit weird and wonderful. A couple of them don't really follow the trend, so they've got excesses at 70 microns, so they are debris disks, never mind what you think about the 160 micron flux. And we've sort of seen 7 of these candidates. And whilst, yes, you could cry galaxy contamination, and that has been an issue with a lot of our sample due to the depth we're going to with these Herschel data, it's, for the chances of this all being galaxies everywhere, that's very, very low. So the phenomenon is real, but which objects we picked out as being real are real, that's going to have to be left to future observations. And so just to illustrate the point, there's a range of plausible parameter space in terms of the dust grain size and the mass of these objects that could be allowed as being plausible disk masses and grain size distributions for these objects. So more importantly, disks and planets, as we heard from Mark's talk, that planets are the more important part. I would beg to argue, I think the dust's more exciting. But I think I'm in the minority. Here we have a poster on this by Virginie Faramaz, PhD student with Jean-Charles. And here we have, again, 100 microns, got some faint emission at 70, sort of becoming brighter at 100, and 160, similar thing to 100. This is sort of cold dust around Zeta Reticuli, which is a nearby disk, and it seems to be sort of a very asymmetric disk, we interpret this as, around this star. And so in order to get an asymmetric disk, you have to have a planet, so we believe. So if you put various types of perturbers into various orbits around the star with a disk in between, you can end up with an outer planet perturbing the disk or an inner perturber to get some sort of these resonant structures in the density distribution. Or you can have a slightly lower eccentricity one, lower mass one, sorry, rather, and you get a slightly more long-lived disk, a slightly lower halo. And yeah, it's a nice example of her. Please go and see her poster. Finally, so looking at the stellar parameters, we see a few trends between the presence of dust and the presence of and the properties of the star. And interestingly, we see an increasing radius with age across all spectral types. Again, you have the red blots are K stars, blue are F stars, and the green ones are G stars. And yeah, so we see expanding disk size with age. This is based on the black body temperature. So these aren't all resolved. And from this, you can say, well, okay, you might get dynamical stirring that's causing the disk size to look bigger at larger ages. Again, see a decrease in terms of the dust flux versus fractional velocity, rather, sorry, not dust flux, dust fractional velocity versus age. So disks get fainter as they get older. Fair enough. And finally, we seem to see a correlation between the temperature and the age. So they seem to get colder, which is probably related to that one. It's an anti-correlation between those two. And finally, so looking at some correlation between the disks and the planets, this is in conjunction with debris. We've sort of pooled our resources and pulled together some radial velocity planets from both our surveys. And we see, interestingly here, this is again similar kind of thing. So the fractional luminosity seems to drop off with age within huge error bars due to low number statistics. And we see here in the middle plot, you've got these, I should probably explain what the dots mean, don't I? Yeah, okay, so solid dots in blue are low mass planets, solid dots in red are high mass planets with disks. The triangles are upper limits on the dust, but red ones have high mass planets in wide orbits, green ones have high mass planets in close orbits, so hot Jupiters, and the blue ones have low mass planets. But as you see, it sort of takes a split about 0.2. You see a lot more dust around low eccentricity systems, planet systems, than you do around high eccentricity systems. So that's probably to do with the planets disrupting the belts that produce the dust we would observe. And finally, if you check stellar metallicity against the presence of dust and the presence of planets, you see that there's kind of, as Mark pointed out with his G-stars, there's low mass, the correlation between low mass planets and presence of dust that he picked out from his 61 Virginis work we see a similar kind of thing in this aggregate sample. So all the low-mass planet star hosts have subsolar metallicities, and they are much more likely, sort of 5 out of 9 stars with low-mass planets have dust rather than sort of, 4 out of 17 or 18 that have high-mass planets in wide orbits. So very much a case of there appears to be a trend, increasing trend between these low-mass planets and the presence of dust and the stellar metallicity, which is consistent with this core accretion theory, that with the low metallicity dust you get greater penetration of the stellar radiation into the protoplanetary disk. So it's not as shielded, so it gets dissipated quicker, and therefore you end up with a much fainter disk. So much fainter disk around later ages. So I'll leave my conclusions there, and I'll let you ask me some questions.
Questions?
Clear as mud.
Stan.
Thank you.
So the no dependence on spectral type of your frequency of detections is rather curious based on what we know now. Is this because you're finding these colder disks, or can you set some sort of confidence limits on this? Or
if we go back to this one, yes, this one here. Yes, this one here. You see here the upper limits we're getting here. If you take a flux limited survey, you're chopping off a lot of these. So if you take a flux limited survey, you're sort of chopping off down here. So you're missing out on a lot of the disks down here around which are going to be fainter around the cooler stars. So you're losing some of the detections you'd otherwise expect to receive if this was invariant with spectral type.
One more?
So I was wondering if you could say a little bit more about how the contamination rates are estimated, and whether the number source counts for the faint background galaxies are revised based on what Herschel deep observations have shown in the extragalactic community, or if they're still based on Spitzer source counts.
Very much, and certainly for the contamination instance I quoted, it's all based on the Burst et al. Paper from 2011, along with the Sipthorpe et al. Paper that came later based on the debris survey coverage of contamination. And so it's all within Herschel, these number counts that we're developing. And within the sample, the size of dunes, sort of 130 odd stars, you would expect to see around about 7 or 8 contaminated sources. And we pick out 7 that are clearly contaminated sources. And of course, this isn't, we know that there are debris disks in this sample, infrared excess stars in this sample. So it may be that some of those turn out to be galaxies, which they did for some of the Spitzer disks. So you do lose a few that way, and you learn a bit more with the higher angular resolution. But broadly speaking, we're consistent with the expected contamination from the Burst et al. Numbers with the numbers we get from our survey.
Okay, let's thank Jonty.